Okay, welcome back. Today we're going to talk about nonlinear dynamics. So that's sort of a ridiculous thing for me to say because you can take an entire semester's course on nonlinear dynamics. You could spend years talking about nonlinear dynamics. So this is really a crash course. For some of you it'll be basic, but I hope I'll give you a couple views into nonlinear dynamics that are particularly relevant for the class. And forgot to hit record, sorry. And I'll put us all on a common footing so we have the same definitions that we're going to make use of throughout the course. So the particular goal today is to, in addition to giving the definitions, I really want to build your intuition for nonlinear systems and what they can do. I want to help you love nonlinear systems and respect, I don't want to say fear, but somehow just know that there's a lot of things that can happen with nonlinear dynamics that you typically don't have to worry about when you're thinking about only linear systems, okay? So we'll use a number of examples throughout the lecture today, but we'll actually spend relatively a lot of time on the simple pendulum. That's sort of what we're going to use as our anchor for the course, for today. So simple pendulum is got a mass here, a length, an angle theta, gravity's down. It's simple because it's a point mass. That's sort of the main simplification. We're going to assume that the rod is massless and we just have a point mass. Okay, so the great thing about simple pendulum is that the equations of motion are trivial, right? So you can easily write the total energy of the system. If you just know the velocity of the mass, then that's enough. You get 1/2. If you work it out, it's ml squared theta dot squared is the total kinetic energy. And then the potential energy, I've got it so my coordinate system theta is 0 at the bottom. So it's going to be, I'll put 0 potential at horizontal, so let's call it negative mgl cosine of theta. So I've got negative potential here, positive potential at the top. Okay, and if you pop that into our standard machinery, which again you don't have to know, but I don't want you to fear for the course, is you can just pop this into the Lagrangian tool chain and come out with a set of equations, of differential equations that will govern the dynamics of this system. So what comes out is if you take the Lagrangian of this, you get ml squared theta double dot plus mgl sine theta equals some generalized force Q. Okay. If my dots are ever not clear back there, I sometimes do them too quickly, just holler, okay? And in general, is the font size okay? Can people see? Yeah? Great. Okay, so there's a lot of things we could potentially do, but let's take our generalized force, right? This is the generalized force. It means the force in the generalized coordinates. So in this case, it's a torque at the base, really. So this is, I wrote it as Q. I'd often write it as tau up there, okay? So let's choose, for today, choose a couple things to model with Q. We'll choose Q to be some resistance due to damping. We'll put a little damping into the joint. So we'll make that just a linear damping term, some friction. Okay. And then let's say I have a motor there that can also contribute a torque. So I'll have some, let's say motor torque, and I'll call it U just to stay consistent. That's our input, right? So that'll be our motor torque input. Okay, so the equations you really ought to care about here, I'll move this to the other side. This is going to be our equations for the day, our main equations for the day, our differential equation. Okay? It might be worth saying, so why are we going to spend some time talking about pendula? Okay, well, it turns out, in some ways, I guess, most of our robots are just a bunch of pendula stuck together. But it turns out to be a nice system because it captures some of the difficulty of the nonlinear systems, but it's so intuitive. We have so much intuition for what a pendulum should do that it's actually, I think it's a really good example. And we'll actually come back to it occasionally to anchor when we have a new control idea. It's helpful to go back, for me, it's helpful to go back and just say, all right, what would that have done on the pendulum? So I really like to use it as an anchor for the course. Okay, so we have equations now that govern the dynamics of the pendulum. This is a second order, it's just a differential equation. Right, so if you put on your 1803 or your some differential equations course hat, then like any good differential equations student, you should think, okay, well, if I've got a differential equation, then the standard problem is if I give you, in this case, since it's second order, I'll give you both theta at time 0, and I'll give you theta dot at time 0. These are your initial conditions, right? And I'll make it easy. Let's say u equals 0 always, so just a pass, so the motor's off. And then the standard question is, what's the solution of that differential equation, right? What's theta as a function of time? How do you integrate the differential equation? So, sadly, even the best differential equation folks will not be able to give you an answer to this problem. It's sort of shockingly embarrassing in some ways that, we can't solve the differential equations that govern a simple pendulum. Okay, right? So in special cases, if the damping is 0, then it's an elliptic integral of the first kind. So it doesn't have we know it doesn't have a solution with elementary functions, but you can evaluate it numerically if you like, if that's useful. If you put damping back in, it gets even harder. So it's not to say that. So there's no simple solution to this problem, and you're just not going to get a lot going down that avenue. Okay. So while this is very much just a differential equation, some of your classical tools that you might expect for differential equations are not going to be the way that we're going to penetrate and understand the long-term dynamics of the system. Okay, so solving explicitly for theta as a function of time sort of feels like the wrong question. It's a good question, it's just too hard. It's too hard for most of our robots. Okay. I can simulate it numerically. If I need to evaluate it, it's fine. But for analysis and understanding, it's hard. Okay. So instead, we have to ask different questions. So we can say, like, what happens as t goes to infinity, for instance? That's a question that we'll be able to get our handle on, right? For the pendulum, you can sort of guess, if I've got a pendulum with damping, you can sort of guess where it's going to end up at time goes to infinity, okay? But what if I if I put in some constant torque? You can figure out where it's going to end if I have some constant torque. The answer is actually a bit richer than you might think. If I have a constant torque, depends on what the torque is, of course, right? So we're going to knock that one out of the park today, okay? So the goal here is, let's give some general tools. For the long-term dynamics, for understanding the long-term dynamics. Okay. There's a couple. It's actually a fairly short list, and we'll add to the list later in the term as we build up. But one tool is linearization. We won't do much of that, but I'll tell you when it's relevant. You can linearize the nonlinear system and look at the properties of the linear system and learn some things. We'll try to be clear about what you can and can't learn. But you might throw away all the good stuff if you just linearize, right? That's sort of not the goal. There's another tool, which is some of you might have seen, many of you might not have, which I particularly like for building our intuition. And I'll call this graphical analysis. And let's do some graphical analysis today. There's actually a great book on nonlinear dynamics by Strogatz. It's cited in the notes. Highly recommend it. Steve Strogatz from Cornell. I'm going to try to channel Steve for a little bit here, give you his beautiful pictorial view of nonlinear dynamics. Does the justification, motivation seem clear? I mean, it's really sort of sad, right? I mean, I can't solve the differential equations for a pendulum, and I'm supposed to make a humanoid robot walk around. It's humbling what we can't do with our robot equations. Okay, so we're going to use the pendulum equations first. Just to have them back on the board here, I'll write them again. All right, let's start even simpler. Okay, I want to think of the case of heavy damping, so an overdamped pendulum. Okay. Make the second order system even simpler. So roughly, I want the case where the pendulum can do all kinds of interesting things. So actually, it's kind of funny. I used to bring a pendulum to class and do all this with the hardware pendulum. And I'd bolt it to the table, and I'd run it from my computer. And I remember the day that I said, I actually said the words, and if I change this parameter to this, the system will be unstable. And I said that, and we had practiced it in lab with all the safeties that would turn it off at the right time, and somehow those safeties weren't on in lab, and I threw a pendulum across the room, basically. It spun itself up and pulled itself free from the table and started flying across the room, only to be stopped by thank God it was plugged into the wall. If it was power autonomous, I don't know what would have happened. But so now I just sort of shake my arm around. It's not as good. I've got a MATLAB thing we'll use in a little bit, but it's safer. So what's that?
It doesn't fly out of the computer.
It doesn't fly out of the computer. Yeah. Yeah, that was really silly. Okay, so let's make this a little bit simpler. I want to think of the case, in general, pendula can do lots of interesting things. I don't want any of this. I want the case where the system is heavily damped. Okay, so I want it to be like, kind of slow and pretty much get rid of all the oscillations. So, M is my mass, L is my length, B is my damping term. Okay, so roughly I want B to be big. So I want, so let's be a little more careful than that. I guess what I want really is, I want my B theta dot term to sort of be much bigger than the contributions from my ML squared theta double dot term. Okay, so to be careful, so if you want to pick a parameter regime where that could be, where that's a safe assumption, One of the things you do often in a nonlinear dynamics case would be dimensional analysis. You could do some quick dimensional, you could right, so B and ML squared have different parameters, or different units, right? Because this one's multiplied by 1 over seconds, this one's by 1 over seconds squared. So to make them in the same units and make some general statement beyond the specific current theta dot and theta double dot, I need some, I want to put in something that makes the units match, right? So, so I can use a characteristic time constant. This is just an aside, sort of. For the pendulum, the standard characteristic time constant is sort of the period of the pendulum. We use square root of L over G. So to get the units right, what I want to say is that, you know, my system is really overdamped if B times square root of G over L is much, much bigger than ML squared. Okay. So if, you know, if I'm in this parameter regime where this is true, then for most, you know, for any characteristic trajectories of the system, this will be true. Okay. It's just a useful aside, is that thinking about units and can help you make more general statements about the systems. Okay. So why do I want B theta dot to be greater than, you know, the contribution of B theta dot to be greater than ML squared theta double dot? Well, roughly that allows me to simplify these equations. So now I can approximate, I can say BL ML squared theta double dot plus B theta dot. Well, that's roughly just B theta dot, right? I wanted that to dominate. And B theta dot, it's got to equal then the rest of that, which is now U minus MGL sine theta. Okay, so if I've got a lot of damping in the system, something nice happens. I can start thinking about my second order system as a simpler first order differential equation. Okay? This is an approximation, and it's valid sort of when my damping is large relative to my inertial contributions, okay? And this is going to be even easier to think about, of course. It's a first order system. Does that make sense? The reason it's worth simplifying it to a first order system is because then I can completely understand everything with a simple drawing, okay? I can tell you everything about what that system's going to do, how it's going to change with parameters, you name it. Everything's just a simple drawing. So the drawing we're going to make here is, let's just plot theta dot as a function of theta. Okay. So what's it going to look like? Let's even set u equal to 0 first, just to keep it really simple. So now it's going to look like theta dot is MGL over B, you know, negative sine theta. So it's basically going to look like a sine wave, right? Okay, with amplitude MGL over B, right? Let me even make one more simplification. Let's forget about the fact that this is an angle and it's wrapping around. That's sort of a complexity we can think about later, but it's not central to what I want to do. So let me even just forget about wrapping, and just to be really clear about that, I'll write Bx dot MGL sine x, just to just so we stop thinking about it as an angle, because that's not central to what I want to say here. So I'm going to just think about it like that for a minute, okay? Okay, so my claim is from this picture, you should be able to tell me everything that can happen about the pendulum. All right, so this first order nonlinear differential equation does a lot of interesting things. The first thing you can say is that whenever x dot equals 0, that's important, right? That's here, 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 you name it. Those are the fixed points of the system, right? Those are the fixed points. We often denote them x star, or I denote them x star, okay, as a fixed point. It means if I start my system in that place, it's not moving. X dot is 0, it's going to stay there forever. So those cases are easy to solve. We're done with those. But the nice thing is we can do much more with this. This is, the simple case of a one-dimensional system on a one-dimensional first-order system. We can do more. We can look and say that, okay, well, when the system's in here, x dot is positive. So the system's going to move wherever it starts. It's going to move that way. Okay. When the system's in here, x dot is negative, so wherever it started in this interval, it's going to move that way, right? And I can just go through and draw that everywhere. And now you can see that, well, I know, given any initial conditions, I can tell you instantly what the long-term solution of the system is, right? So if I started in here, I'm going to move this way and end up at that fixed point. If I start here, I'm going to move this way, I'm going to end up at that fixed point. If I start very, very close to this fixed point, I'm still going to end up at that one over here. Right? It's completely, there's no mysteries here. So these fixed points where you end up from a large range of initial conditions, we're going to call those stable fixed points, and we're going to shade them in my little diagram here. And the ones that you move away from are going to be unstable fixed points, okay? There's even more I can throw in. So I'm going to be a little bit more careful about stability fixed point of the fixed points too. Let me just write down as I say. There's even more that we can talk about just for this picture. There's a very useful idea in nonlinear systems, which we don't really have in the linear systems, is I could talk about the region of attraction to this fixed point, okay? Or the basin of attraction of this fixed point, which is the set of all initial conditions that if I started simulating my system there, it'll end up at this fixed point, right? So it's the set x such that if x0 equals x, then x infinity equals x star, or the limit as t goes to infinity, x of t equals x star, okay? So the great thing is I can draw it easily on the diagram. I always bring colored chalk for this lecture because it gets crazy. Is that going to work? Is that sufficiently distinct from yellow and visible? So the region of attraction to this fixed point is somehow, well, we know it's going to be have its boundaries here. And in fact, that's a pretty general idea, actually, is that the regions of attraction are often defined in part by passing through some unstable equilibrium. It's more complicated in high dimensionals, but certainly in the one-dimensional system, it's true. So this whole region here, which is really just the region on this line, but I'm going to color it in because I want to make it look grand, right? It's just a one-dimensional thing. That whole thing is the region of attraction to this fixed point, right? That interval. And then the boundaries of the region of attraction are called the separatrix. We're almost done with all the definitions, but I want to throw them out, even casually. They're defined more carefully in the notes, but I just want to build up the language. Okay. So this is great. So we know already, just from looking at this diagram, that I can, there's a bunch of things that happen over here. They all go to this fixed point. There's a bunch of all the initial conditions here go to this fixed point. All the initial conditions here go to this fixed point, so on and so forth. Okay. So that's not unique to pendula in any way. There was nothing about that that took advantage of the fact that that was a sine wave or anything like that. I could actually apply that analysis to any nonlinear system. And it's really interesting to think about the different types of behaviors you can get, right? It's limited on the one-dimensional systems in a nice way. But if you even get to two-dimensional systems, it gets very rich very fast. Okay? So let's be a little bit careful about stability now, okay? So you've probably thought about a bit about stability of linear systems before. In a differential equations class, you probably thought about systems that looked like that. So if you make a flow sort of diagram, if you plot that, there's only a few things that can do, right? So depending on the values of A, right? So I can get a value like this. I can get another, this is, let's say, for A equals 1, sorry, negative 1. If I had A equals, I don't know. Or I could maybe a special case is A equals 0. Right? But there's only a few things it can do, right? So first off, every linear system of this form has a fixed point at the origin, right? And then the question is really just, is that fixed point stable or unstable, or what, right? And you can see instantly, graphically, that if A is less than 0, then what? Is it stable or unstable? Right? If A is greater than 0, it's unstable. And then if A equals 0, it's called marginally stable. Okay. The nonlinear systems are much richer than that. They don't need to have a fixed point at the origin. They can have fixed points anywhere. They can have lots of fixed points. They can have no fixed points. Those fixed points there's lots of different types of stability, in fact, that they can have, okay? So, I mean, you could have systems that are stable from one side and unstable from the other side. You can have systems that are sort of they're stable by some definitions of stability, but not by all definitions of stability. So let's be a little bit more careful about nonlinear stability. It's not stable or unstable is not enough. For instance, what happened if I drew a diagram, that went like this and just kissed the origin? Is that stable or unstable, right? And what if it kisses the origin with a slope of 0 right there, right? Or even if it goes like this, is that stable or unstable, right? Well, you kind of want to say that that's stable. Things are going to go there, but it's kind of going there at a rate of 0 when you get close. So we got to be careful about that. What does that mean, right? Like maybe to accentuate it, what would you say about a system that was like this? Right? Is this fixed point stable or unstable? Well, that's a little bit different, right? So we're just going to have to be more expressive. All right? So let's talk about the stability of a fixed point, which is also called local stability. Okay, a few more definitions to throw at you, but they're all good to know, okay? And you might know some of them before. So I'm gonna write them in shorthand here. They're written more carefully in the notes, okay? But first definition is we're going to say stable in the sense of Lyapunov. Which is often shorthanded as ISL. If for every epsilon small, right, there exists some delta greater than 0 such that if I start my system pretty close to the origin, so I want this to be a distance, it can be Euclidean distance, it could be some other distance. I want the distance between my initial condition and the fixed point to be less than delta, implies that the system's never going to run away it's never going to be more than epsilon away from the system, from the origin. Okay, so that example I just gave here, where it's even flat here. Let's talk about the stability of the fixed point at the origin. Is that stable in the sense of Lyapunov? Right? What it says is that it's a game, right? If you you tell me an epsilon. I have to be able to find you a delta, right? So you say, I want to guarantee that I'm never going to leave this interval, and I'm allowed to pick any interval that's close to the origin. I have to be able to find you some delta, which presumably is going to be smaller than epsilon, such that if I start in there, I'm never going to leave your interval. If I can't play that game with you, then the system's not ISL, right? If I can't find a delta for every epsilon you could choose, then the system's not ISL. In this case, for this system, choosing delta equals epsilon is my algorithm, and that's fine, that'll work, but it's harder than that in general, okay? Does this notation make sense to everybody? Somehow the distance between my system at time 0 for whatever initial condition, right? So this would be in general a ball in a higher dimensional space. And this is saying for all t, it's going to be it's going to be inside some epsilon ball. I'll take silence to be passionate acceptance. So there's more definitions at play though, right? So you want to somehow be more expressive than that, because that's stable to Lyapunov, but it's not really stable to everybody, right? I mean, there's clearly things that I could ask for that are more than that, right? Let's say I wanted to actually get to the origin at some point. So there's a definition of actually getting to the origin. All these are locally asymptotically stable. If I actually get to the origin as time goes to infinity. This one's not asymptotically stable, right? My pendulum was asymptotically stable, and we'll see more of those distinctions. Yeah.
Is that for all x, or could you?
So this is when I say locally, the slightly more careful thing would be to say is that for some small epsilon, if I start with x0, this is sort of subject to x0 is x star plus epsilon. And then if I were to remove local, you can have global asymptotic stability, which would be for all x. Yeah?
That's true for epsilon, for any epsilon greater than 0, or?
For epsilon implies small for my, yeah. Yeah. It only has to be true arbitrarily close. Yeah?
In this scenario, do we have multiple fixed points? Because where's that?
So this is by virtue of making it an epsilon argument, this is now immune to the problem of multiple. So I can ask this for any one of those fixed points. So if I have lots of fixed points, then I'm just asking in the small neighborhood around that particular fixed point, am I going to converge, right? And then the broader, harder problem is what can I say about all x or big swaths of x? That's sort of my region of attraction question. But just let's just say first we're zooming in on around any one fixed point. Tell me what happens. Does it converge or not?
Yeah, I'm specifically talking about when it's flat.
Okay, when it's flat, I would actually say that this has got an infinite number of fixed points along there. And any one of those you pick would be stable in the sense of Lyapunov, and none of them would be asymptotically stable. Yeah?
Could you repeat the questions?
Good. So I'll repeat them from now on. We're sort of recording this one just for you. If we might post it or might not post it. We actually didn't need to record this one. We just figured it's worth. It's not too hard to record it. It's hard to edit them. But we might just throw them up raw if you guys miss a lecture or want to watch again something. Okay, there's still even more sort of refined definition of stability that you might want. Maybe you don't just care if it gets there as time goes to infinity, maybe you've got a schedule, you know? Maybe you want to say, I'm going to get there in some reasonable amount of time. In fact, linear systems will never get to the origin in finite time, but a nonlinear system can. It could actually get there in finite time. It can also escape in finite time if things are going bad. You know, so there's all kinds of richness. But a typical thing that we talk about in stability is getting there on some schedule. So the last one we'll do here is x star is again locally exponentially stable. If we basically want to bound the rate of convergence, right? So I want this number to sort of go down on some schedule. So I need to be able to find some c greater than 0 and alpha greater than 0. Such that that distance is going to get smaller on a schedule, right? So it's going to converge at least exponentially fast. All right, that's the idea of exponentially stable. All right, so does exponential stability imply asymptotic stability? Yes. If it's exponentially stable, then the limit will also get there as time goes to infinity. Does asymptotic stability imply Lyapunov stability? That was tough. I would expect most people to say yes. That's a perfectly reasonable initial answer, but nonlinear systems are hokey. They're actually distinct definitions. And if there's time by the end, I'll make sure I'll give you an example, and there's certainly an example in the notes of a system that is, they're just distinct notions. You could have a system, what would it have to look like, right? A system that, if it starts arbitrarily close to the origin, in many cases it converges to the origin, but at least in some cases, in some ways it'll run away, and run away arbitrarily far, more than epsilon away. And I'll give you, you can't do it in 1D, I don't think. I couldn't think of a way to do it in 1 dimension, but in 2 dimensions, when we get to it, we can draw pictures that'll do that. Okay, so those are sort of separate chains of analysis. There will be places where they overlap, but you can be stable in the sense of Lyapunov, and roughly that's probably a more encompassing set of systems. But you can find quirky systems that are asymptotically stable that are not stable in the sense of Lyapunov. Okay, so let me just do another sort of graphical example. So I think one of the fun ones, so I actually did my PhD with a neuroscientist, a computational neuroscientist. His name was Sebastian Sung. It was fantastic. He taught me a lot about dynamical systems and math. From the context of neuroscience, actually. One of the systems that he liked to study, and actually, just so you believe me, maybe, there's one of his papers, for instance, the AUTAPS, okay? A simple illustration of using, let's just say, of using simple dynamical systems, like we're doing here, to talk about memory. Okay, so the idea is that I'm going to write a simple differential equation. It's going to roughly model some concept of a neuron in the brain, and that it's a hypothesis for the way that the brain can store short-term memories by keeping activity alive in your neurons with feedback loops. Okay? So it's pretty cool to think that, we can draw a couple pictures on the boards of and say something about memory, I guess, okay? So let me tell you just a little bit more. So the way people model neurons, if you're a mathematician, starts off very simple. There's many more detailed models than this, but the one rough view of what a neuron does if you're mathematically inclined, is that it basically takes a bunch of inputs. We'll call them U's since that's our standard input. And let's say it's a vector of inputs, and this is the first element, second element. Okay, they're coming in on wires on the dendritic on the dendritic spines. You know, there's some synapse or whatever that you're getting a signal coming in, and each of these signals coming in has a different sort of gain. And then you get something in here that combines those signals and gives you an output. Okay, so a lot of times we model the inside as some and some rectification kind of term. So, you know, one model for this would be something like tanh of the sum over I of Wi Ui. Okay, so I sum in all my inputs, weighted sum, and then I put it through a tanh. Tanh, if you don't know, is this sort of nice function that goes like this. Just sort of a sigmoidal function that rails itself at +1 and -1. Okay, and has the slope 1 at the origin conveniently. Okay. All right, so that's roughly, very roughly, what a neuron might look like in the brain. And for a long time, people were talking about really just as this is a function, you know, an output that's a static function of the input. But then there was this trend of starting to think about neurons as dynamical systems. Okay, so a slightly richer model of a neuron might be, we can give it some dynamics. So we can say that there's the state of the neuron is X, and we'll give it a dynamical system that looks pretty similar, but okay, so it's the same. I'm getting a bunch of inputs from my neighbors, and that's going to somehow increase my activity, and then I have some sort of leak rate, which is actually roughly models the loss across the ion channels of the potential in the cell. Okay, so that's a simple now dynamical system that if I start giving the system input, it'll knock it'll ramp its activity up. If I let it go, it'll come back down to 0. Yeah? Guess what we're going to do? We're going to understand everything about this system. But let's make it a little simpler first. So the AUTAPS is a particular dynamical system where I'm basically going to take a single neuron. Of course, the interesting thing about neurons is there's lots of them, and they can make lots of different rich connections. We're not going to do that yet. We're going to just take our input around our output and stick it around and put it into our input, and just not worry about these other inputs. Okay. All right. So we're going to make a recurrent loop back to our input. It turns out that seems like a sort of a hokey thing to do. We're actually not sure if it happens very much in the brain, because it's really hard to tell where all those wires are going in the brain. That's actually a big theme nowadays, is trying to understand where all those wires are going. So we don't really know if neurons connect to themselves very often in the brain. They do in a dish. So one of the weird things we do is we take a few neurons out of the brain, we stick them in a dish, we let them regrow, and they're sort of sad because they don't have any of their friends around, so they just start connecting to themselves, and then they start spontaneously firing and they come back into sort of a healthy, possibly completely irrelevant compared to the brain, but with some sort of network of activity emerges again. So certainly in a dish you can see these AUTAPSes, they're called, self-connecting networks. And I just Googling AUTAPS, here's an example of that's a electrode coming down, a glass pipette with an electrode in it coming down from the side, that's what the blurry thing is, of a single neuron in a dish that has, because of, doesn't have any friends, is connected to itself and just stimulating itself. Okay, it's called an AUTAPS. So let's think about why an AUTAPS is sort of an interesting idea for memory. We could think about it by drawing, it's doing graphical analysis. Yeah? So, do it right here. Okay, so let's plot x dot equals negative x plus tanh wx, right? So if I have it loop around with a single connection, just to write that, then my equation is just that. A single feedback loop, okay? I can plot that. Right, so negative x looks like that. And then, so I got some contribution from that, and then I've got that tanh that's sitting on top of it, so it goes between -1 and 1, so it's going to be somehow look like this, right? It's my tanh. Yeah? Something like that, okay? So depending on w, of course, but let's say that's my okay, so what are the fixed points of that system? Got the zero, yeah, any zero crossing. So roughly, so there's one at 0, there's one at roughly 1, getting close to 1, and one at -1. Okay, are they stable or unstable? Is this one stable? Right? This one's stable? No. This one's stable. Yeah, good. Okay, so now you can maybe see why people are thinking about this as a sort of a memory type phenomenon, right? It's a lock, it's a latch, right? So if I kick it up in activity, I have a fixed point over here, right? And the activity will persist at a high level of activity. If I were to somehow push it back down past here with some exogenous input, then it'll latch over here. It's a very simple neuron model, and it's got sort of latching memory. That's kind of cool. It's the particular type of memory and the stability properties of that memory will depend on W. Right? So the way you can encode more complicated things with a network of neurons is by changing W. So what happens if we change W here? Right? So right, that's going to take my tanh and make it sort of steeper or shallower, right? So if W is small, it'll look more like that. And W is steep, it'll look more like this. So if I change W too much, if I reduce W too much, I could actually end up with a pretty different system that does something like, I shouldn't have done that from that angle, okay, but something like that, right? And now my fixed point is at the origin only. That's a stable fixed point, but there is no latching memory, just for a smaller value of W, right? So the parameter dependence of nonlinear systems and their stability properties comes up all over the place, and there's tools for that too. We won't use them too heavily, but I want you to be familiar with them, to have seen them at least. So there's something called bifurcation analysis, okay? Analysis, but I'm going to draw a bifurcation diagram. It plots behavior of fixed points as I change a parameter. So the aw taps, what I'll plot here is the parameter change, which is my feedback gain W. And I'd like to plot x star, the locations of my fixed points, as a function of that parameter W. Okay? And this one just, I mean, so it happens that it's helpful to know that tanh of x roughly looks, or even tanh of wx looks roughly like wx for x near 0, okay? So what that tells me is that the inflection point here where, so something magic, this doesn't happen in linear systems, right? I can change my parameter and fixed points can be created or destroyed, right, with a simple change of parameters. That's power. You can change, you can destroy fixed points of systems, right? So that magic happens for this system when W equals 1. That's the critical point. When W is smaller than 1, that's when the slope of this line just happens to kiss the axis, right? When W is smaller than 1, I have a stable fixed point at x star is 0. Right? The only fixed point I have is at the origin, and it's stable. And then as I increase W through 1, that fixed point gives birth to two fixed points, which start walking away from the origin in this way, which I only know from plotting. Okay, does something like that, and asymptotes to 1 and -1. And a new fixed point is born, or there's still a fixed point at the origin, but that's an unstable fixed point, so I'll draw it with a dashed line here, okay? So again, so the point is just that these cool things can happen in nonlinear systems. It happens, you'll see people talk about bifurcation diagrams. It's not going to be a huge tool for the class, but I want you to be familiar with that this kind of thing can happen. Okay, this one happens to be called a pitchfork bifurcation diagram, and there's all kinds of great names. So if you're in nonlinear dynamics, I guess maybe one of your charters in life is to try to come up with a new type of bifurcation. There's blue sky bifurcations. There's all kinds of funny names for bifurcation diagrams. Okay, that one's pretty common, pitchfork bifurcation. Okay, so magical, cool, we can see everything we want about pretty complicated general nonlinear systems just by drawing it. If it's one-dimensional, first order, then I can do everything with a picture. All right, so sadly, robots are second-order systems, and they're multivariable. So we're going to have to do a little bit better. So let's ratchet it up a little bit. Oh, I forgot. So what happens in the pendulum, still in the first order case, if the parameter I change is u? So let me just draw x versus x dot. Remember, I have the diagram of, this was my u equals 0 case. X dot equals negative MGL over B sine theta, right? But I have a U there too. So what happens to my fixed points as U, as I start changing U? So what's going to happen to the curve if U becomes slightly positive? The whole curve is going to slide up. My fixed points are going to move. They're going to start coming together. Okay? So what does that have? That corresponds to, I have a simulation for this too, but I'll just do it from there. So, so if I start applying a little bit of torque in the overdamped pendulum, my fixed point at the bottom is going to start moving I'm applying a little bit of torque, like this, and it moves, it'll find a balance against gravity where that torque matches gravity, right? And I'll see it, I can see it as I increase U more and more, it moves this way and this way. Until there's a critical thing that happens. What happens when my fixed point hits there, right? When U exactly equals negative mgl over b? Yeah. That's roughly what happened in my demo before, right? It starts going around like this. You can make it even worse than that, of course. Right? My fixed point disappears. Right? I could draw the bifurcation diagram. Did we ask you to do the bifurcation diagram in the problem set?
Yeah, just as a plot for yourself.
Yeah. So there you go. So you can just see what happens. Now there's another fixed point sitting in the system, right? The unstable fixed point. It's also moving, right? So this unstable fixed point is the fixed point at the top, which if you haven't stabilized it is unstable, right? You start there, you fall away. That's this fixed point over here. It starts moving in. You might not know sort of intuitively where it goes, right? But as I start applying the torque, then actually it's sitting like this, right? They start coming together. Right? So the unstable fixed point is actually hanging out here, again, where my torque would balance gravity, but in an unstable way, right? Until they come together, and then I start going like this, right? So you can understand everything about the pendulum with a picture like that. It's great. Okay. Except for the fact that not all pendulums are super uber damped, right? I mean, damping is, okay, so there's a lot of systems that actually are first order, right? So if you care about fluid dynamics, right? If you talk about low Reynolds number of flows, then you're thinking about things moving in molasses and everything becomes first order and Stokes' theorem, and you've got a good life of first order analysis, and you can draw pictures and you can prove theorems. Yeah, but if you've got inertia and that matters, then we got to think about at least second order systems. Our graphical tools for second order systems aren't as good, but they exist, okay? So back to where we started, which is the second order equations. So how do you plot? Now this is, what I see when I'm looking at this. Really, you can always write the second order system as a first order system in two variables, right? So if I define my x as theta and theta dot, right? Then I can write my system as a first order system, f of x, which is going to be theta dot, and then my dynamics here. So right, so one way to think about the second order system is really as a first order system in two variables. You've seen that before. Okay, but this is also how we're going to think about plotting it. Okay, now we have really a vector valued differential equation, right? Over two variables, right? So the way I have to plot it now is I have theta and I have theta dot. And at every point, theta dot, I can figure out what x dot is, my vector valued function. It's got it's a vector of two variables, so I'm going to draw it as an arrow in this spot. Right? So for every point, I can evaluate this, get a vector out, and draw the vector, and that's my vector field, right? This is called the phase portrait or vector field of my system. Okay, so that's the way we're going to draw them. It's harder, but it's totally doable. You get used to it. So we can draw it for the pendulum. So I want to make sure that sticks. It's sort of, if you've seen it, it's easy. If you haven't seen it, I've had times where I thought I said that in an intelligent way, and then people just didn't get it. So does that make sense? Why would you draw a vector? Yeah? You got two values coming out of your differential equation. And roughly, it very much corresponds to, if I'm in this state, what direction am I going to move? Okay? So let's draw the vector field for the pendulum. And start asking about its stability properties if it's a second order system. Okay? So let's do B equals 0, U equals 0 first, just to start our engines up here. So theta dot. Now, if I were to walk along theta equals 0, then it turns out the vectors are very easy. They have, so let me draw it and then see if I've convinced you. But it turns out, so at 0, I plug 0 into that, I get 0 back. Okay, so I've got a point there. If I go to theta's a little bit positive, sorry, theta dot is a little positive, theta is 0, then what I get is something that has only a component in theta dot. And if I walk along this line, this axis, that should be a line that goes through the origin, that's just theta dot coming back out. And similarly this way. Okay, that's a bunch of vectors that were easy to plot. The other one that's really easy to plot is I can walk along where theta dot equals 0, and then I just get my MGL sine theta coming out. And it's the x component is 0, and the y component is negative MGL sine theta. So I get something that the magnitude is a sine wave, right? And similarly over here. Okay. And I have and then in between you get some combination of those two things. So I'll get vectors that look like this in between. Yeah.
Wouldn't it make more sense to label the axis with two labels? Because for the vectors, you're basically assuming then the theta axis is now theta dot. And the theta dot axis is our dynamics equation.
So the units of the vector,
yes,
they start at a particular theta and theta dot. And I agree that what I'm plotting here is effectively the x coordinate is theta dot. Yeah, sticking with tradition, the long tradition, I think the right way to label it is like that. But absolutely, the x coordinate of this vector is just theta dot, and the z coordinate is my theta double dot. Yes, I totally agree. Right? Okay, so now let's look at the picture and where are the fixed points of the system in a phase portrait? What do I have to look for fixed points?
You don't see any arrows.
Yes. but there's another, but it has to be even more than that. Well, sorry, I guess it is that, but you'll never get one, for instance, when theta dot is positive or is non-zero. So you can only have no arrows along this axis for a second order system, right? But what you said is perfectly true. And so that happens here and here and here, which are the same, pi repeating fixed points of the pendulum, okay? Now if we fill in, if we were to simulate the system and follow a trace, an orbit of the system, then you're going to see things that go like this, right? And then this one, they actually go that way, right? They go around this fixed point, which is the same up to the wrapping. But right, so this is the sort of the famous eyeball of the pendulum. Okay. And then it's maybe more interesting, actually, what happens out here, too, is that this one will go up and around and then bounce off, sort of, and keep going. That's the spinning around and around case. Okay, and again, we can sort of see everything that happens in the pendulum just by following these, making these plots. So, is this fixed point stable? Exactly, right. So the question is, your answer should immediately be that's a bad question. You got to be more specific, right? So is it stable in the sense of the Lyapunov? Yes. Yes. Is it stable asymptotically? Not if there's no damping, right? It'll oscillate forever around the origin. In the zero damping case, it is not asymptotically stable, nor exponentially stable. Only stable ISL. Okay? And these are not even stable in ISL, of course. Those are unstable. Okay, there's plenty to know about evaluating the stability of these things just from visualization. Okay, you can imagine. So I'm going to budget my time here. If I put in damping, then what happens? I get a little bit, basically every time I add some velocity, my vectors are going to shift a little bit down. My acceleration is going to be slightly negative due to velocity. So all of the vectors are just going to take a little bit of a slant this way, okay, back towards the origin. And what does that do? That means that the orbits of my system end up with this spiraling behavior that comes like this. And you can see it all from the vector field. That's with damping. That's if B would be greater than 0. Okay. Now, if you wanted to evaluate, so you might ask, is this system somehow stable given damping, in the sense of Lyapunov, in the sense, is it exponentially stable? All these questions. There's limits to what you can do graphically. At some point, the more general way to assess asymptotic or exponential stability is via linearization. You can do that in high dimensions, and we'll repeat as we use them the conditions. But basically, if the nonlinear system, just to say it once while you're thinking about it, if the system is exponentially stable, the nonlinear system is exponentially stable, then its linearization must be stable. If the linearization is stable, then the system must be exponentially stable. If the linearization is marginally stable, it has any zeros, then actually we know it's not exponentially stable nonlinear, but we don't know. It could be asymptotically stable, it could be unstable, we don't really know. And then if the linear system is unstable, so there's all these conditions. If the linear system is unstable, that guarantees the nonlinear system is unstable. The goofy case is if you get linearizations that are 0, it could still be asymptotically stable. It might be even asymptotically, or it could be unstable. You just don't know from the linearization. Okay, but since I'm almost out of time, let me finish with this, the really, really important point. So you can do almost everything graphically, but we don't just care about watching pendula in the class. We aim to do control, okay? So let me give you this view, given this viewpoint of thinking about dynamics and thinking about flows and long-term behavior, okay? This is what I want you to think about going forward in the class, all right? How does U enter this equation? If I have a control input, a control torque, right? So U can only affect my theta double dot coordinate. U can make my vectors go up and down, right? Doesn't actually affect the other direction, but I can affect my dynamics this way. Given U, I can do a lot of things to change my vector field. U doesn't have to be a constant. U can be a function of theta and theta dot. So I can put a different correction on this vector versus whatever. I can only ever move it up and down. Given that power, I can do a lot of things, right? I can take this eyeball over here and move it over here, right? I can make my pendulum go upside down. I showed you how to do that with feedback linearization. But if you think about what you're doing, you have to put some pretty big U's in a lot of spots to make that happen. So here's really the way I want you to think about control, right? You've got some vector field that you want. What the name of the game is, find the small U's, because that's good. It's less energy. It's less susceptible to model error. There's all these good reasons to do less, to let the physics rule, okay? The name of the game is going to be, how do I choose U as a function of position and velocity so that I can just tweak my vector field, not overpower it, not erase it and put my new one in. I just want to twist it a little bit to bend it so that all of these arrows, all this flow goes to the place I want it to go. That's the name of the game. It's a computational game. It's a game that we're going to play with a lot of different algorithms, right? We're going to find ways to compute U, to change this vector field in a minimal way so that the system ends up doing exactly what we want, okay? That's the view of control I want to have in this class. And it all comes down to pictures. I mean, we're gonna go back to like even pendulum pictures at the end for complicated algorithms, just to make sure we understand what's going on. That's the goal.